to binary to decimal conversion. So sometimes we may need to learn how to convert a number in base 10 to binary format in base 2 and vice versa. This is because computing devices usually compute data in binary format, and hence, to understand what takes place, we may need to see it from the binary perspective. Cisco's devices permit you to impute IPv4 addresses as 4 octets of decimal numbers, like 192.168.10.50, or more expressively this way, in 8-digit octets. But the network devices recognize the IP addresses as 4 octets of binary format base 2 numbers, as we can see in the example. So we need to practice how to convert a number which is base 10 to binary format in base 2 and vice versa. So from this table we can see that we have the octets given, and these octets represent numbers, as you can see at the far right. Like if you see at the bottom of the table, you can see 3 is this way in 8 digits, and 304 is this in 8 digits. So 8 digits represent an octet. So this is an octet. So we can see that this 3 million we have at the far right here is the same as this at the far left in octet representation. So if you want to convert this one, which is 3 million, you will take the first digit, which is 0, and you multiply it by 10 raised to power, which is the base number raised to power 0. So the first digit takes a power of 0, and that's what we have here. So you do the same thing, the second one, which is 0, second 0, you put it here 0, then you take the raised to power 1 and you multiply it, and you continue doing it that way. You can see the number here, which is 3. Remember, this is base 10, so you can use any number from 0 to 9. So in this case we have 3, which is here, as 10 raised to power 6. That's 1, 2, 3, 4, 5, 6, 7. So it's meant to be here. So that's why we have 3 times 10 raised to power 6. So if you add up everything, you will see that it will give you the eventual 3 million. So what we've been able to prove is that the 3 billion, which is in octet form, using the method of conversion to base 10, you would get the same 3 million in base 10. And if you do that also for 300,000 and 30,000 and down to 3, you will see it's the same thing. You just take the position of each digit, and the first one is 3, so you put it 3 times 10 raised to power 0, which is 1, and that's 3, and the rest, you know, it will be zeros, because 0 times anything is 0. So what you have here is 3. So let's look at 2 examples. So in this example, we've been told to convert 236 in base 10 to base 10 in decimal. So we just want to confirm that this indeed is a base 10 number, and when converted to base 10, it will be the same thing. So if you put that by the side, 236 is equals to this in 8 digits. That's the octet format. So we can see this is in 8 digits, the octet format. So the same one is, you now take from the first position, or let me say the last end of the octet, and that one will be 6, which is here, times 10 raised to power 0. Remember from our table, the last one always is 10 raised the base raised to power 0. Then we have 3, which is here, 3 times the base, which is 10 raised to power 1, as we can see here. Then we continue that way, 2 times 10 raised to power the base 10 raised to power 2, you see, and we continue that way, and eventually we get back our 236. So this has proven that our initial 236 is actually a base 10 number. So let's try one more and see. So this time we have a larger number, and we are told to convert, this is 1,200,440 to base 10, which is to decimal. So we convert that to octet, to an octet, that is 8 digits, and that's what we have here. And we follow the same process. So we start from the end, which is 0, and we say 0 times the base, which is 10, raised to power 0, 4, which is the next one, times the base, which raised to power 1, then the next 4, which is the next one, times the base raised to power 2, and we keep going that way, and eventually when we add all of them up, we get back our number. So we can see that we've proven also that this is actually a base 10 number by converting it to a base 10 number. So let's talk about base 2, which is binary. So we need to convert binary, which is base 2, to decimal. So we're going to use the same format, the same table, but we just changed the base number. Remember, we used 10 in the initial one, but this time we are using 2. So you can see 2 raised to power 0, 2 raised to power 1, and 2 raised to power 2 down to 2 raised to power 7. And this time we have 2 raised to power 0 is 1, 2 raised to power 1 is 2, 2 raised to power 2, 4, 2 raised to power 3, 8, 2 raised to power 4, 16, down to 2 raised to power 7 is 128. And now we are given the octets of binary numbers. Remember that binary only accepts zeros and 1, 0 and 1. So unlike base 10 that accepts 0 to 9, but this is just 0 and 1. So that's why you can't see any other number here apart from 0 and 1. So you can represent it in octet form too, and that's this way. So we're going to find out what this octet means in decimal. So we're going to use the same process to convert it to decimal. So remember, in the process we use the counted from the end, which is 0, which is here, and we multiply it by the base number exponential 0, and we do the next one, 0 here, the base number exponential 1, 0, which is the third one, the base number exponential 2, and we keep on going to the last one, which is 0, the base number exponential 7. That's what we have here. So if you multiply all that and add all of them up, what you get for this first one is 64. And you also see the next one, what we will get to is 32 and down. So what this means is that this binary number 01 0000000 is actually 64 in decimal number. So let's prove that by doing some examples. So this is our first example, and we're going to convert 000001011, which is a base 2 number, to a base 10 or decimal number. So we'll use the same process. We'll put the number there, which is the binary number, which is equals to, then we'll start from the last one, which is 1, and remember we multiply it by the base number exponential 0. We add it to the next one, which is 1, by the base number exponential 1. We come to the next one with 0. We add it to by the base number exponential 2, and we keep going to the last one, 0, and we multiply by the base number 7 and add it to the rest. So that's what we have done here, and eventually we end up with 11 when we sum them all up. So what this proves is that conversion of a binary number 00001011, which is in base 2, to a decimal in base 10 will give us 11. So let's try another example. So this time we're going to convert an IP version 4 address, and we've been given as 11000.000101010.0001111 to base 10. We have to convert it to base 10 decimal. So to solve this, we're going to split them into octets, because that's why they are separated by the dots. So IP version 4 addresses are actually 4 octets that are separate, that are joined together by the dots. So we'll take the first octet, and if you take it here, we use the same process. We start from the last number, which is the last digit, which is 0. We come down here because this 0 times the base number raised to power 0, exponential 0. Then we take the next one, 0 times the base number exponential 1. We keep doing that till we get to exponential 7, which is the 8th digit. 1 times 2 raised to power 7. Then we multiply all that, which is 128 plus 64, then zeros, because anything multiplied by 0 is 0, and when we add everything together we get 192. So to convert 1 and all zeros in binary to decimal will give us 192 in decimal. So the second octet, which is what we have here as 0 ones, is equals to the same process. We'll take the last one, which is 1, the last digit, which is 1, and we'll multiply by the base number, which is 2 raised to power 0, and we do the same thing the next one, which is 1 times 2 raised to power 1, and we keep going till we get to 0, 0, 1, 1, 1, 1 ones to decimal will give us 127. Then we do that of the third octet, and we can see that we use the same process. So all this will give us this 8 plus 2, and we have 10. So converting this binary will give us 10 in decimal. And the fourth octet, the same process. So our decimal conversion of 0001111 gives us 15. Hence, when you bring them all together, remember the dot notation is what separates them. So you bring them back all together and you get is now 192.127.10.15. So this is the decimal representation of the IP version 4 address. So how do we now convert this decimal to binary in base 2? So we use the same table, but we just change a few things. And the first thing we change is we just, instead of multiple, we add this subtract. So also by the side we can see a condition. It said is it greater or equals to, and down here we can see our first number, which is a decimal number we have to convert to binary, which is 50. So how does this work? How do we use this table? So what we do is that we first get the decimal number we want to convert, which is 50, and with this table this way, because we took like this table from the other one's table that we used, what you do is you pass this 50 first to this first argument, that is this first portion of the table, and you say is 50 greater or equals to 128, not minus 128, 128, you know. So is 50 greater? No. And you say no, so that's why we have 0 here. This 0 means false or no. So 50 is not greater or equals to 128. So that's why it leaves 0 as false at the bottom here. So why do we have this dash? This dash is meant to be where the remainder should be once you've subtracted the number from 50. But in this case, because the number is greater than 50 and doesn't fulfill this condition, then you have no remainder. So you are not performing any operation there. So that's why we have this dash. So we take the same 50 to the next column and we say the next number we have there is 64. And we say is 50 greater or equals to 64, and we know that is not true. That's why we have 0 down here. So it's false. And the same thing, we don't have a remainder because we didn't perform any operation, so we'll have this dash here. Now there's another condition we must consider, and it's not right here, but we need to consider in our mind, and that is that this 50 also must be less than the previous column. So if you're trying to take this argument 50 with 64, we can see that 50 is not greater than 64, so it doesn't pass in this case. But we can see that 50 in the next column is greater than 32, as we have here. So that's why we have 18, because since it's greater, we've put 1 here, which is true, represents true as a yes. Then we now take the operation and say 50 minus 32 will give us the remainder 18. But before we do that, we must consider what is before it. That's the 64, which we considered before. You know, we must consider that this 50 is greater than 32, is greater or equals to 32, but is less than the previous one, which is 64. So that's just the new additional rule you must consider, that if you're going to carry out the operation, you must be certain that the argument is greater than the 32 in this case, and is less than the previous column, which is 64. So what we have as a remainder is 18, and we had 1 here because 50 is greater than 32, and that's why we carried out the operation that gave us the remainder 18. So the next thing, instead of taking that 50, we take 18 this time, and we'll take 18 as a new argument, and we'll move it to the next column, and we'll say is 18 greater or equals to 16, and in this case we know it is true, so we put 1 here as a yes. And the same question is 18 less than the previous column, which is 32? Yes, it is. So we will go carry out the operation and say 18 then minus 16 will give us the remainder 2, and that's why we have the remainder 2, and this one, remember, represents that 18 is greater than 16. So instead of taking 18 again, we take this 2, which is the new remainder, the remainder, and we take it as the argument to the next column, which is 8 here. So we'll say is 2 greater than 8, or greater or equals to 8, and definitely no. So we'll put 0 here because it's false, and we put dash here because there's no operation that will take place since 2 is not greater or equals to 8. So we'll carry the same 2 as an argument to the next column and say is 2 greater or equals to 4, and we know it's not. So we'll put 0 again as a false or no, and we'll put dash because no operation has taken place to give us a remainder. So we'll take the same 2 again and move it to the next column, which is 2, and we'll say it's 2 greater or equals to 2, and yes, 2 is equals to 2. So that means we put yes, which is 1. That's true, which is 1 down here. And we'll carry out the operation. Remember, we also check that this 2 is less than the previous column, which is 4, which is true. So we'll carry out the operation and say, therefore, 2 minus this 2 will give us 0. So our remainder will be 0 because 2 minus 2 is 0, and there's no remainder. So we'll put 0 as the remainder. So at this point, we can take this 0 and move it to the next column, which is 1. And we'll say, is 0 greater or equals to 1? No. So that's why we have 0, which is false, and we have dash that because no operation was carried out and no remainder was given. So at the end of that, we'll just take this all these numbers of 1s and 0s, and we'll just concatenate them together to form the new binary we have here. So the summary is that 50 as a decimal number is in binary form is 00110010. So I know it's a bit tricky, but I know that if we do more examples, you would get to understand what actually the method entails. So let's try the next one below, and it says we should convert 164 which is a decimal number to binary, and we'll use the same process. So remember, we'll pass the condition whether it is greater or equals to the number given in the column. So in this case, we'll take 164 to is it greater or equals to 128, and we'll say yes, it is actually. So that's why we have 1 here, so it's true. But remember the second condition, that it must be less than the previous column. Right here we don't have a previous column because we only considered an octet, that is 8 digits. But assuming we consider 9 digits, maybe the 9th digit would be 2 raised to power 8, and it will give us 256 here. So it means that if we considered 164 to 256, is definitely lower than 256. So this will be true. So we'll take the operation and say 164 minus 128 will give us 36, which is what we have here. So for the next one, remember we always take the remainder and we take 36 and we'll now compare it with the next column. I'll say it's 36 greater or equals to 64, and no, that's why we have 0 here, it's false. And because we don't carry out any operation to give a new remainder, we'll put dash here. And we'll take the same 36 to the next column. Is 36 greater or equals to 32? And definitely it is. So we'll put 1 here, which is true or yes. And we'll carry out the operation and say 36 minus 32 will give us 4, which is the new remainder here. So this 4 is what we'll take now and say, is 4 greater or equals to the next number on the column 16? And we say no, it is not. So we'll put 0 and no operation is taking place, so dash. Take the same 4, compare it to the next number in the column, which is 8. Is 4 greater or equals to 8? No. So we'll put 0, it's not, which is false, and dash no, because no operation was taking place. So we say 4 again, is it greater or equals to the next column, which is 4? Yes, 4 is equals to 4. So what we do is that we'll put 1, which is yes or true, and then we'll say 4 minus that 4 will give us 0, which is the operation. So it gives us 0. That means no remainder. So we take that 0 and move it to the next column and say, is 0 greater or equals to 2, which is false. That's why we have 0 here, and no operation is carried out. That's why we have dash. And same 0 we take again to the next one. Is 0 greater or equals to 1, which is false, and that's why we have 0. And the same thing is dash no, because no operation took place. So by the time you concatenate all this together, what we'll have as 164 decimal will give 10100100 as binary. So let us try one more example and see how that works. So this time we're going to convert the IP version 4 address 192.127.10.15 to base 2 binary. So to do that, we have to divide the IP address into 4 octets, and the first one being 192, the next one is 127, the next is 10, the next is 15, because each octet is separated by the dot notation. So let's come down here. We can see the first octet, which is 192. So we'll take it through the same process, which is 192 greater than 128, which is yes, true, and that's why we have 1. And eventually, if you say 192 minus 128 will give us 64, and we'll take 64 now to the next column. Is 64 greater or equals to 64? Yes, 64 is equals to 64. So you have true, which is 1, and a remainder of 0. Then you take 0 to the next one. Is 0 greater or equals to 32? Which is not. That's why we have 0. And no remainder. That's why we have dash. And the same thing onwards. We have dash and 0 dash 0 dash 0. So eventually converting 192 to binary will give us 11000000. So for the second octet, which is 127 in decimal, we need to convert that. So we compare it with each of the column, and we say, is 127 greater or equals to 128? No, 127 is less than 128. So we'll put 0, which is a no, and dash because we didn't perform any operation, so no remainder. So we'll take 127 again to 64. Is 127 greater or equals to 64? Yes, 127 is greater than 64, and that gives us 1, which is a yes. And is 127 minus 64 will give us 63 as a remainder. So we'll take 63, the remainder, to the next column, which is 32. 63, is it greater or equals to 32? Yes, it is greater. So that's why we have 1, which is true. And by the time we subtract 32 from 63, we get 31. And we take that remainder again to the next column. Is 31 greater than or equals to 16? Yes, it is greater than 16. So that's why we have 1 here. And the same thing, we take the subtraction, 31 minus 16 will give us 15. And the same thing, 1 Is it greater or equals to 1? Yes, 1 is equals to 1, and that's why we have 1 here as true, and 1 minus 1 will give us the remainder of 0. So that's why we have, if you concatenate all that, you get 0, 1, 1, 1, 1, 1, 1, 1, which is what we have here. So for the third octet, we do the same thing. So you do the same for the fourth octet, and what you end up with is these are the binary. And now by the time you bring everything together, you see the first octet, the second octet, third octet, and fourth octet. Hence we have the IP version 4 address in binary format as given here. So that is the simple method of converting from decimal to binary and binary back to decimal.